Continuing with our AP Statistics final presentation is Chapter 2, which is describing location in a distribution. To start off is measuring relative standing and density curves through standardized values, which allows us to compare different data sets on a common scale. An example is SAT scores and ACT scores, and then Z-score is also introduced, which is how many standard deviations of value is above or below the mean and can be calculated by doing value minus the mean divided by standard deviation. And then complete set of Z-scores for the distribution always have a mean of 0 and standard deviation 1.
So an example problem is math SAT scores have a mean of 500 and a standard deviation of 100, and calculate your Z-score. So let's say you got a 650 on the math SAT section. So what you do is you take the 650, which would be your X value, like your personal score, and then you subtract the mean, which is 500, and you divide that value all over 150, and then you divide it by 100, and you get 1.5. For a percentile, it's just a value with P% of the observations less than or equal to it. So if we said that Medfield High School is in the 94th percentile for high school graduation rates, this means that 94% of all high schools have the same or lower graduation rates than MHS.
Also, our density curves, which have many characteristics. First is they describe the overall pattern shape of a distribution, and they're an approximation of it. They are always on or above the x-axis, and the area underneath always equals 1. And then the area probability proportion is what they represent. The area under the curve is proportion of all observations falling in the interval. And then to the diagram on the right, there are 3 different types: symmetric, skewed to the left, and skewed to the right. The ones that are skewed to the left has a left tail, and skewed to the right, a right tail.
When talking about density curves, it's also important to know that they do not always take on the shape of a curve. In these 2 pictures, the density curve is drawn in a uniform distribution, which is when it takes on a constant value 1 over an interval from 0 to 1, and is an outside range of values. 0 is an outside range of values. And the data described by this distribution takes values that are uniformly spread between 0 and 1.
So for measuring mean and median of a density curve, for median, it's equal areas on either side of the distribution, and it cuts the graph into 2 equal pieces, and this is resistant to outliers or skews. While on the other hand, mean is the point on the curve where the curve would balance. So there's equal weight on either side, and this is not resistant to outliers or skews. Symmetric of a distribution just means like mean equals median, and when a distribution is skewed, the mean is pulled towards the tail.
It is also important to distinguish between parameters and statistics. The parameter describes a population. It starts with P, both of them. Population and parameter start with P, so that's how you can remember it. Statistic describes a sample.
This slide describes how to perform exploratory data analysis with your data. So you start off by plotting your data and making a graphical summary. Then you look for a pattern in your graph to describe the shape, center, spread, and outliers, and convert that into a verbal summary. Then you calculate the center and spread and create a numerical summary. And then describe it using a smooth curve, and especially when the pattern of large numbers of observations is regular, meaning that it will create more of a symmetric and unimodal model. The mathematical model is an idealized description, so it gives a compact picture of the overall pattern of data, but ignores the minor irregularities and any outliers. An example of this is a line of best fit or a smooth curve.
So some characteristics about normal distributions is that they're all symmetric, they are single-peaked or unimodal, they're bell-shaped, they're described by the mean and standard deviation, so you'd write n and then mu and then standard deviation value. The mean equals the median, and the mean is located at the center directly below the peak. The median is how spread out the curve is, and inflection points are the points at which a change in curvature takes place, which is seen right here.
Normal distributions are used in a lot of different ways. They are good descriptions for real data like SAT scores. They're a good approximation to different kinds of chance outcomes, like tossing a coin. And then many statistical inference procedures are based on the normal distribution. But you have to keep in mind that not every symmetrical distribution is normal.
When the distribution of data is normal, it is important to take note of the empirical rule. This rule describes how, in a normal distribution, 68% of the data falls within one standard deviation of the mean, 95% of the data falls within two standard deviations of the mean, and 99.7% of the data falls within three standard deviations of the mean. And that's kind of shown in the picture to the right here, showing a normal distribution on a graph and showing the proportions of the numbers to the standard deviations.
So for standard normal distribution, the equation is z equals x minus mu over standard deviation. And to this specific type of distribution, you define it by n01 for the mean and standard deviation. And if the variable we standardize is normal, then the new variable z is also normal.
When drawing normal distributions, you should sketch the curve, mark the z value, and shade the area of interest, which is the area below the z value, and then use the table in your pink packet, which shows what the area is below the curve. And then greater than and greater than or equal to are the same.
To find the specific percentages of the area under the curve or to find a specific value on the curve of a normal distribution, there are a few calculations to know. So when finding a percent probability or area under the curve, you start by stating the problem in terms of x and drawing a picture of the graph. Then you standardize the value. Then you use the table in the pink packet to find the certain percent probability or area that correlates with the z-score that is known. And then you write your conclusion in context. When finding a specific value on the curve, you state the problem in terms of x and draw a picture of the graph. And then use the table in the pink packet to find the percent probability or area that is depicted on the graph in order to find the corresponding z-score that is unknown. And then you unstandardize the unknown value that you found and write your conclusion in the context of the problem.
So this is what the table A looks like in the pink packet. And basically, once you find the z-score using the equation, you can look at the table to find the value by looking at the left column and on the top column. The percentile represents the percent of data lying below the z-score, which is found inside the table.
With normal distributions, you can also use them on your calculator. To find a percent probability or area, you use normal CDF, left bound, right bound, mean standard deviation, and then finding a specific value is inverse norm percent below, which is area, mean standard deviation. And then for assessing normality, there are two methods. The first is to construct a histogram, sum plot or box plot, looking for the shape, while the other is looking for linearity with a normal probability plot.
And to wrap up chapter 2, we have an example problem that requires a standard normal calculation to solve. So we start off knowing that the percent of observations of the standard normal variable are greater than negative 2.65. So we draw a graph of our normal distribution with a mean of 0 and standard deviation of 1 and shade all of the area above negative 2.67. And then we can find the percentage of the observations by subtracting the area below negative 2.67 using normal CDF from the total area of the distribution, which is 1. And if you don't have a calculator, you can also find this value using the pink packet to find the percentage below negative 2.67 and subtract that from 1.